Let me kind of introduce the problem of what image restoration is. So image restoration at a high level, the goal is to recover high quality images from degraded or corrupted observations. And so here we see two examples of this, where we see corrupted images that might be a blurry image, which might be taken because someone, was moving the camera when they took a photo. Maybe if you have a robot that's kind of going out and taking images in the wild, the images might be blurry. This is an example of where the image has some haze added to it, which is typically the case when you take images in foggy environments. And the goal of image restoration is to kind of get rid of these corruptions or degradations. And so kind of formally, we're going to speak about these as measurements Y. And the goal is to kind of reconstruct some sort of clean version that we call X that has removed this corruption. And to kind of formalize this problem, we're going to assume that we have some sort of mapping that kind of characterizes what the actual corruption process is. And this is captured with this nice forward equation. And so what this says is just that your measurement Y is going to be some function A, which we're going to assume is known, of the clean reconstruction X that I have, plus maybe some additive noise that might be assumed to be Gaussian. And so for these two examples, for the deblurring example, we might know that the blurry image was obtained by applying a specific blur kernel across my image and involving my image with that blur kernel, or maybe some hazing operator that kind of models how light scatters in a foggy environment. And so this is the kind of setup for the problem. And why is this hard? Well, the main challenge is that this function A is typically not invertible. And so this means that actually getting X from Y is very ill-posed. And so if I give you an image that's like really heavily corrupted, then there could be many possible reconstructions that kind of lead to this measurement Y. And so how do we really deal with this kind of ill-posedness of the problem? Well, there's two main ways to tackle this in the literature. The first is an optimization-based approach, where typically you just search over possible reconstructions X, while saying that you're going to kind of want a reconstruction term that measures that it should be consistent with the measurement that I'm given Y, while also maybe maximizing the prior of X under some prior distribution. So this could be, some sort of sparsity prior or various other priors, including like generative model priors on X. And the second approach, which is what I'm going to be focusing on today, is kind of the more popular approach these days, is to kind of leverage the power of generative models and approach this in a Bayesian manner, which is saying that I actually want to sample from a distribution that is P of X given my measurement Y. And we're going to treat our model or forward equation model as a model for P of Y given X. And so in the case where I added some Gaussian noise to it, this is typically going to be some sort of Gaussian distribution that has mean A of X and has some sort of additive noise to it. And we're going to focus on this today in the context of where I want to sample from this distribution using the diffusion model. And so before I kind of tell you about how we're going to use diffusion models to do this, I'm going to kind of briefly recap how these diffusion generative models work. So at a very, very high level, the goal of these unconditional sample models is to generate a sample from P of X, right? And so X is some distribution here over images, and I want to train a model that will sample from that distribution. And the key insight of the diffusion model is that we're going to start with an image that's purely noise and kind of progressively denoise it over many steps in order to get a distribution that looks like a sample from the clean data distribution. And more specifically, what diffusion models posit is that instead of knowing access to the distribution P of X, which we don't know, if we had access to the score function of the distribution, which is really just the gradient log probability of that distribution, then we can generate samples from the distribution. And there are kind of mechanisms to kind of learn this score function from data that I'm not going to get into in today's talk. But we're going to assume that we have some sort of model that can sample from the distribution P of X. And so if I now wanted to sample from the distribution P of X given Y, Y, recall, is our measurement, we can kind of clearly extend this by rewriting this stochastic differential equation, which is a function of our unconditional score function. It now becomes a conditional score function, where the score function is now computed on the distribution P of xt given Y. Here, xt represents the tth iterate of this process that we call the reverse process of the diffusion model. And so nice, we have a kind of way of formulation to generate samples from P of X given Y. But of course, we don't know this score function. So the kind of obvious thing that one might do is maybe we'll just retrain our diffusion model. We're going to collect a bunch of data samples. In the same way that this model was trained, we might retrain that conditional score function to sample from the distribution P of X given Y. And people have done this, it works reasonably well. But what's the problem with this? I mean, the main problem is that you need to now have a diffusion model to generate from every single task that I have. So if I have a deblurring problem, then I need to have a deblurring diffusion model. If I have a dehazing task, I need to generate a dehazing diffusion model. I need to collect a bunch of data, train that. It's super expensive. And so the kind of name of the game is how can we do this without retraining these models from scratch, and maybe using these like pre-trained unconditional models that are really good at generating pretty pictures. So this is the kind of the way that these insights, the insight that allows us to do that is actually decomposing this conditional score in a very clever and neat way. So what's written here is just on the left-hand side, we just see the conditional score that we had on the previous slide. That's what we want to have access to. And if we had access to that, we could sample from the distribution P of x given what. And here I'm just rewriting it using a simple application of Bayes' rule. And what we get now is two terms. One is this unconditional score. Recall that this is the nice term. This is what was already modeled by my pre-trained diffusion model. So this part is great. We already have access to this. The second part is something that looks like what we call a noisy likelihood score. It really depends on this distribution that is P of y given xt. And so the hope is, okay, well, we knew our forward model, right? That's P of y given x is 0. We know what that is. We can say that that's a nice, clean Gaussian distribution. So maybe we could use that to somehow compute this score function by maybe just taking the gradient of that. Turns out it's not so easy because xt is actually the result of this very complex denoising process. And so kind of mathematically speaking, this distribution P of y given xt kind of factorizes over all possible x zeros, which corresponds to all possible denoised versions from a given xt. And it kind of depends on the distribution P of x0 given xt. That's in fact the distribution that we're trying to sample from. And so it's very expensive to generate samples from this and approximate this integral. So, what people usually do is approximate this integral in various ways by saying that, okay, we don't know the whole distribution, and it's hard to kind of get samples from it, but we might be able to construct kind of poor man's estimates of it. So the kind of leading approach is that since if we don't know the whole distribution, we can still kind of get access to statistics from that distribution. More specifically, you can compute what's known as the posterior mean, the expected value of x0 given xt, using kind of a neat formula called Tweedy's formula. And maybe you can construct some sort of simple distribution centered at this mean, which is precisely what some prior works do. So these are kind of two examples of approximations that are made. The first is known as diffusion posterior sampling, or DPS, where you just approximate this distribution P of x0 given xt as a delta distribution with mean that is this mu 0 given t, which is precisely the posterior mean. And then maybe you can also make a normal distribution and so on and so forth. So kind of what are the main challenges from doing this, right? Because we did this, we made this kind of approximation, this very poor man's approximation to this distribution. This can actually make the intermediate results of my diffusion model fall off this manifold that's being learned by the diffusion model as I do this kind of iterative denoising process. And so this kind of leads us to our main research questions in our work, which is, can we kind of understand the limitations of these popular methods if we introduce these types of approximations? When is this approximation error high? And then the second question is, can we actually design new algorithms that will provably mitigate some of these approximation errors, but also empirically work well at kind of solving these kind of image restoration tasks? And so the kind of key insight that I want to maybe spend a second on is looking at what we call the frequency analysis of the diffusion models. So this is an insight that's been observed by various other researchers in different groups, and it's a very neat idea. The idea is simply that if we want to kind of understand what happens when you approximate this noisy likelihood score, we need to first understand what happens in the actual diffusion process training. Namely, what is the structure of our iterates xt, right? And so let's start with the simplest case, which is when t is 0. x0 is the nice clean image, let's say, from our data distribution. It's kind of well known that natural image data, if we look at the frequency characteristics of it, then it tends to follow what's known as the power law in the frequency domain. More specifically, what that means is that if I plot frequency versus the magnitude on a log-log plot, it's basically linear. And so it means that the image is roughly dominated by a lot of its low frequency components, which kind of dictate its overall structure, and kind of high frequency details kind of exponentially drop off in this plot. And so this is a phenomenon that's kind of widely observed and has been known since like the 1970s, right? And now if we look at other time steps in the model, because your model is operating on isotropic Gaussian noise, which also has a kind of isotropic across all the frequencies distribution, you can kind of characterize what the intermediate process looks like. Namely, if I have a very noisy image, then it's going to be dominated by the low frequency components, and the high frequency components will be masked out by the noise that I'm adding. So intuitively, what this is saying is that when I start from pure noise, I'm left with an image that's just pure noise. It's noise isotropic across all the frequencies. But then over the course of my diffusion process, when I'm progressively removing the noise, I'm going to start by generating the low frequency components first, and then later on kind of refine the high frequency components. And this is the kind of structure that's been empirically observed, and it's been well observed for this, how diffusion models generate images. And so using this, the kind of obvious insight is that this is how the diffusion model is going to generate stuff as we follow the reverse process. Now, if we introduce this kind of extra gradient term that follows our noisy likelihood score estimate, if it makes changes to the parts that are heavily dominated by noise at that term, right, then in some sense, you're kind of destroying the structure that the diffusion model has been expected to during its generation process. And so how can we kind of induce this artificially? Well, we can kind of look at a case where the frequency of your measurements y kind of automatically mismatches what the diffusion model is learned to generate. And so here we see kind of two examples of this. What is being shown here is that we have some sort of clean image of a person. The way that the measurements are generated is one of two regimes. One is when you apply what's known as a low-pass filter to X, namely means that you preserve the low frequencies and you kind of curtail a lot of the high-frequency components of your image, and you generate a measurement. This is kind of like a blurry image. This is how Gaussian blur operates. And the kind of contrasting way is if you take an image and apply a high-pass filter to it. A high-pass filter is one where you primarily preserve the high-frequency components like edges and so on, and you kind of get rid of some of the low-frequency components or heavily reduce them. And as you can see, here we see three different baselines. I've only spoken about DPS, but there are some other algorithms that do image restoration, and they work kind of reasonably well for the low-pass filter setting. But when the operator is a high-pass filter, you can kind of see that they all really miserably fail, especially this one. And the algorithms really don't work at generating clean, nice-looking images that are able to restore something that mimics the ground truth operator. And this is kind of directly inspired by what we saw in the previous slide. And so to fix this, what we propose is a super simple modification. The idea was that our estimates to this noisy likelihood score kind of push your gradient in the wrong directions. So how can we avoid that? Well, since the issues are with the kind of high frequency parts of the approximations to the noisy likelihood score, maybe what one might do is to just transform the measurements such that at the early stages of your reverse process, you only keep the low frequency components of your measurement and then slowly add in the high frequency components as you go on. And this is kind of an artificial way to restrict the gradients of your noisy likelihood score to be kind of aligned with what the unconditional scorer has been used to, right? And we call this algorithm as frequency guided posterior sampling. So really it's a very simple estimate of this, which still uses a kind of poor man's distribution for that distribution P of x0 given xt, but it fundamentally changes the way that the measurements are fed into that algorithm using the structure of the diffusion process that we know. And so based on this, we wanted to see whether this algorithm works in two regimes. One is in the theoretical regime, where we can kind of understand, precisely play around with what's happening, and then one empirically. So in the next two slides, I'm just going to briefly detail that without going into too many details. So the first part of our work is kind of performing a theoretical analysis, where the goal is precisely to understand, we have this approximation errors that accrue over your reverse process. What exactly are these approximation errors, and can we quantify them? And particularly since we've made such a big deal about analyzing the frequency components of our data and so on, then we would ideally like our analysis to include some of that frequency analysis of your data. And the kind of short TLDR of this slide is that we like multivariate Gaussian distributions for theory purposes because it's easy to compute scores and we can kind of exactly quantify what the true conditional score is because we kind of know what the true distribution is, P of x0. But multivariate Gaussians might not have the frequency structure that we want, right? And so this kind of nice lemma allows us to connect the two by saying that you can kind of construct a very specific covariance for your Gaussian distribution such that data drawn from that distribution will follow a power law in the frequency domain, which is kind of the frequency characteristics that natural images follow. And if you were to do this, then you can kind of precisely quantify what the approximation gap is. So, it's easier to understand this if we kind of look at a plot of what's happening. So what's happening here is we're going to, on the x-axis, we're plotting the reverse process. And the y-axis is actually plotting the exact approximation gap in this toy setting that we described for two models. One is the posterior sampling algorithm that I mentioned in the beginning, the baseline, the diffusion posterior sampling, also known as DPS. And one is ours, which just applies a simple transformation of the measurements. And as you can see, this y-axis is on log scale. So this approximation gap at the beginning of the reverse process is already orders of magnitude below what the diffusion posterior sampling approximation gap is. And since the beginning of the process kind of refines the low frequency details of your image, we argue that it's super important that initially the approximation gap is low. Otherwise, it'll kind of not match the fundamental structure of the y measurement that you're given. And indeed, if you kind of go back to this picture that we were looking at, now we've added in one more column corresponding to how frequency guided posterior sampling works on this high pass filter case. And we kind of see that, well, this algorithm gets you something that really does not match the fundamental structure of the measurement. Our algorithm is able to, take this image that's been very heavily corrupted and kind of get you something that's pretty reasonably close to this modulo some sort of slight brightness increase. And then, of course, we've been talking primarily up till now about high pass filter settings, but we argue that this kind of phenomenon of preserving high frequencies is relevant for a lot of other problems. And so here, returning to the true problems that we talked about in the beginning of the talk, motion deblurring and image dehazing, we compare our method to some other leading baselines, and we find that in motion deblurring case, our method is able to kind of reconstruct the kind of finer level high frequency details of your image, whereas a lot of the baselines either don't really reconstruct it, or they kind of remain blurred, or they introduce heavy artifacts, because we argue that this is because of the approximation gap that's kind of incurred over the reverse process. And then on the right-hand side, you also see that you can plot perceptual quality as measured by some perceptual metrics, and our method is able to really significantly improve upon a lot of the baselines through this very simple trick. So just to conclude now, today what I introduced was a method for doing new posterior sampling for image restoration that doesn't involve retraining any diffusion models, and it's kind of able to take off-the-shelf pre-trained diffusion models to restore images in the wild. And the kind of key observation was to use the specific structure of the diffusion reverse process to develop this algorithm, and then we kind of theoretically analyzed it as well as showed some image restoration. That's all. Thank you.
We have time for a question. Anyone in the audience?
Going back to those plots,
Which ones?
yeah, like the plots of power. How do you compute power?
So are you talking about this? Or are you talking about?
Yeah.
So this is in our toy setting. So in this case, basically what this slide says is that you posit a distributional assumption on your data, which is that it lies from a very specially constructed multivariate Gaussian distribution. And because things are Gaussian, right, you can exactly compute what the true conditional true noise likelihood score is, because like I said, this factorizes as this, right? So this is a Gaussian. This conveniently also becomes a Gaussian distribution in the case where P of x0 is Gaussian, right? And so we can exactly calculate this distribution, which means we can actually calculate this as well. And in that case, you can analytically calculate what is the approximation gap. It's a toy setting because we want to just understand what happens in theory. So of course, real images are not Gaussian, but it's really just a theoretical tool to understand a setting in which it kind of mimics the frequency structure that we want, but also shows a gap between existing methods. So,
Yeah.
So you're in this one, you're always assuming that if your model, the function A is known, right?
yes.
Have you explored what happens if that function is not known?
Yeah, so in this work, no, but in general, there's many kind of straightforward ways to extend these to the case where you don't know A. Namely, you can change your algorithm to be kind of an alternating minimization algorithm, where you do one step of updating your XT, and then you have another kind of model for estimating what your A is. So let's say in the case where it was a deconvolution, so it's a blur kernel, you have some estimate of it, so you randomly initialize it, and then you kind of optimize it with respect to your model that's P of y given x0 at each step also. So you kind of alternate between updating XT and alternating and updating the kernel that you have. So you could do that. I think that's been done in other works, but we're kind of focused more on understanding how to improve the actual sampling part of it, not the estimation of the kernel.
So we follow on that, like the process of adding a SFI functional model for it. Or models are not just like a hypothesis.
Yeah, I think so, because I mean, fundamentally, the sampling algorithm, we argue that the issue stems from these approximation gaps, which is kind of tangential to estimating the operator itself. So for any given operator, that should still hold.
Great, let's thank our speaker. And please join me in welcoming our second speaker. Erica is a second-year MSc in robotics at the University of Pennsylvania. She graduated from the University of Michigan in 2023, and after graduation, she hopes to continue to work in the design of mechatronics and control systems for the space robotics industry. Please welcome Erica.
So, as Torian said, I'm Erica, and I'm presenting my research project that I've been working on for the last year and a half, almost 2 years now. It's a really long name, so bear with me. It's trusses, which means temporarily robots unite to surmount standing entrapments and then separate. Really quick acknowledgements I do need to make. I'm here representing ModLab, and this is a NASA-funded project. But to begin with, what exactly do I mean by sandy entrapments? Sandy entrapments and generally sandy terrain is still a prevalent area of research in robotics, especially for locomotion and exploration. In unstructured environments, you're prone to, and in granular material, you're prone to slipping or sliding. You can sink into the material, you're gonna get the material loaded on. You could find obstacles hidden in or ditches or positive obstacles as well, like with rocks or other materials out there. So when it comes to the problem of lunar exploration, we run into all of these problems and more because you have to be completely autonomous there. You have to be able to, make your way around without losing connection or losing traction or any of your locomotive abilities. And this becomes especially tricky if you're just sending one bot up there, whether or not it's big or small, it's still susceptible to all of these problems. And so what the Trusses project suggested is to create a team of robots. So instead of sending just one bot out there, you send multiple. The idea is that if you have multiple and they have this ability to connect to one another, they would be able to help the bot that has gotten stuck and bring them back out. And really quick, also, this is a really, really big project. There are 5 different labs working on this. There is the Sun Lab working on more controls, Mod Lab where I am working on all the hardware, PennSed doing just terrestrial studies. So this is looking into what are the ground, how do you characterize what the ground is as you're walking over it, etc. RoboLand, which is a USC lab, working specifically with robot ground interactions, and then PodLab, who is also supervising all of our efforts here. As I said, I'm working with ModLab, and so I will overview all of the hardware to get to the point where you can get a system that can connect, move each other around, and ideally, by the end of it, pull and save another bot out of that. So really quick, the maneuvers that we wanted this system to have, it's a kind of complicated system. These are some of the 2 example maneuvers that we're hoping to accomplish with this system. Essentially, we wanted to show that there are tasks that the system would be able to do that one bot would not be able to do alone. So let's say it's trying to climb a dune and it's too steep or too slippery for the one bot alone. With our proposed system, another bot should be able to connect to it and then push it up that dune. And then once the top one is up there, it can anchor itself there and then pull the other one back up. Another maneuver we're hoping to do is, like I said, the one that's stuck, it could be stuck, just buried in the sand, it could be in a ditch. And 2 other bots can come, also connect to it, and then pull it back out. Some of the key system properties that we do have to figure out and build is that we wanted to have a heterogeneous team of robots. We wanted to showcase that because different locomotive methods have their pros and cons, if we had a team that could connect between all of these systems, then we could utilize the unique abilities of each bot as the maneuvers are happening. And so the 3 bots that we ended up using for our project were the 2X which is a double scale version of the Rex, which is a COD Lab research platform that has been previously developed. in two modes, one with wheels and another one with legs, closer to its original namesake. It's a hexapod with a tripod tail. I'm not controls, but if you want to ask about that, you can. A small wheeled rover, so that's the what we colloquially call the P Husky, and a Spirit, which is Ghost Robotics legged quadruped. Another property of the system is that we needed to be able to connect into those truss-like structures, and then we also needed it to be able to push and pull within that system. And in order to do that, we have borrowed a little bit of research from Model Lab's previous work with what we call a spiral zipper, and I'll see if I can get this video to play up here as well. But this is the VTT. It's a separate project that Model Lab is working on, where essentially it uses these contraptions are called spiral zippers to change the form of the trusses. So it can connect to one another, and then everything by extending and retracting those spiral zippers, you can change the form. I'll also see if I can. Oh, okay, cool. A little bit more about that. Key properties of the spiral zipper, just for extra background. It's that it has that, again, extension and retraction with a single motor, and it's really good with compressive loads. This is also borrowing from that previous research work that we've already done, and this is the system we use to propose how to connect all of those bots together in the complicated truss-like hardware structure. But the spiral zipper on its own is not adequate. In order to give it like positional control, we had to also build a frame for it. And so what we have called this contraption with it inside the frame is a spiral zipper turret. Essentially when it's inside the frame, we have gained the ability to also have end effector positional control through extension, pitch control, and then yaw control. And then with a couple other added sensors and electronics, we get precise length tracking, and the winch design will also allow for more additional tensile forces applied to the end effector, so it helps us to do those push-pull maneuvers and give it a little bit more strength as it's doing all of that. And so the last year and a half or so, most of my work has been the engineering part of engineering research. Mostly it's been design, manufacturing, and assembly. I focus mostly on designing the 2X Rex and scaling that up, and then manufacturing and overseeing all of the manufacturing and assembly of the 15+ person team that it took to get all of these things actually built. The spiral zipper and turret, again, similarly, I was responsible for a lot of design modifications there, and then also managing the mass manufacture of 5. It's a lot for a research lab, I promise. And so that was like a big chunk of my work. But it was all in preparation to take us to the lunar simulant testbed. So like I said, we wanted to explore lunar exploration. And so we created the system so that we can test all of our bots in NASA Ames's research center, but specifically the Survey lunar testbed. We had a little field trip of 9-ish days out there, where we ran 3.5 experiment just to stress test our system, and then to understand how exactly do our bots interact with this kind of regolith. Lunar regolith, it's because we're not allowed to call it soil because it's on the moon. At this testbed, we have this LHS1, which closely matches the texture and material properties of the lunar regolith that we do see on the moon. And so we ended up doing all sorts of tests out there just to stress test again, understand how our system is working. Those experiments that we ended up doing kind of fell into 3 basic categories. I'm not going to go into the details of these again, but there were some static turret tests where it was push pulling a various range of different weighted payloads. So all of the first row tests here, you can see it was in different formulations and mounting it in different ways so that we can understand all of those properties. The second kind of experiments are static turret ones again, but push pulling our wheeled Rex, which was more difficult than anticipated, but I'll get into that later. And then also just a couple basic capability tests. How does a rover actually locomote over this? How does a wheeled rover look like that? How does a legged rover walk through this? And then can we also understand, part of the research that the other labs have been doing is, will it be able to understand the ground properties just by walking over it? And that's a separate research project, but that was also really cool. They actually got a lot of things from this trip. I do have a couple videos if you guys want. I was just gonna play them. I need to make sure that some of these things are muted and or not muted. But it was just a lot, again, like I said, like basic push-pull tests and a lot of different sand. Something that I did not put on here or mention is the fact that in order to prep the beds and to understand the properties of the sand, both in two different scenarios, we had to prep the bed either by tamping it. So like imagine standing on the sand and then like trying to like compress it as much as possible with a like flat shovel, or fluff it to make it as soft as possible, and using a rake to come in and make it as soft as possible. You can kind of see that the differences between the tamped and fluffy areas on this like bottom image right here. The center is where we tamped that down, and then the back part was where we fluffed it. And then after all of those experiments, we got a couple different really big insights, especially from a hardware side standpoint, like very important takeaways. One, learned a lot about what exactly how LHS1 reacts, or like some material properties of that. Because it is a very, very fine material, one, it makes it really dense. So something we did not expect, say you have a mound of material about like this big, like this much material on the end of a shovel, it felt like it was like 20 pounds, like right here. So just prepping the bed was a lot more work than anybody had originally anticipated. But because it's also very fine, it's very prone to creating all of those dust clouds. So like in this video, this first video, I'll just let it replay. As we were preparing the bed just to run our experiments, it got dustier and dustier. And those also ended up causing problems for a couple of our hardwares, and it illuminated a couple of the issues with our system design at this point. Thirdly, it also compacts really well due to the granular structure of it. It leaves, so one proof of that compaction you can see on the right hand image, it leaves these very fine tracks. It's not like most sand that we see on Earth, where it's loose enough where it will like fall down again, and it won't be able to hold on to the shapes if it's not wet. Most of the time, like if you see sand doing that, it's most of the time because it's wet and it's sticking together that way. But we found out that the LHS1 is also compacting in those ways, and also causing problems because once it's compacted, you're more prone to slipping, et cetera, et cetera. And then just also compacted, it's dangerous to inhale that for long periods of time. So as you saw in the first video, we're all in like complete safety gear, like head to toe, just to be out there. And so some of the things that we took away from that as a hardware team is that because it was so dense, it prevented our spiral zipper from being able to push the loads as much as we wanted it to. And so some of the design modifications are going to be strengthening, making sure that the spiral zippers are now strong enough to actually pull our desired loads through there. We also saw, it showed us where all the stress points were on the turret part, the frame. It showed us where all of the stress points were on that frame. And so again, some of the redesign work will be just strengthening up all of those things. And then because of those dust clouds, it ended up also clogging some of our rotational joints. As the spiral zipper moves forward, there are a couple different lazy Susans. We use a lazy Susan to also control the yaw. And once dust had gotten in there, it started getting clogged a little bit. And we're also working towards fixing that so that we don't see those problems when we move into our further experiments. So I kind of outlined the future work. It's a lot of the system redesign, and then from moving forward, it's more integration and systems testing to get the 3-bot, multi-bot heterogeneous system up and running. A lot more work on the controls and planning, a couple of those things. And then our future experiments, we hope to actually do both of those 2 maneuvers that I had outlined earlier, both the kind of extraction test and one of the June's test that will be up over the summer, and then out in November is going to be our final demo with the extraction one. But it was a really big project, so I had to put an acknowledgement section of all of the people that ended up working with me on this. But that was everything. Thank you guys for listening, and do you have any questions?
for you to get rid of some of the hardware that was dust, of the dust, I know it's carcinogenic, so. And to get rid of that, some of this hardware after you do the testing or.
We cleaned off as much of the bots as we could on the way back out, but with our tight-ish schedule and running experiments like 9 to like 7 most days, it was it was just you clean off as much as you could and then bring it back. It's not really a problem if it's not airborne, and so when it comes back and it's just kind of on the materials, just try not to breathe it in. It's also more dangerous than like the more it is, so if you just can't get it. I'll keep it.
Do you think that sort of aerated dust would be as much of an issue in hypothetical real world deployment, or is that more of something to do with the test bed and we compare it being in such a small area?
Yeah, so a majority of it did come from our test bed prep, but when bots are also moving in it, it will just be on its own kicking up sand. So if the like spirit bot, oh, you can't really see him. He also had to wear pants because of this. But the spirit bot, as it's just kind of walking around in there, it's going to be kicking up sand. If you're running your wheels in there, it's going to be kicking up sand. I say sand when regular just one. It will just kind of get into the air from doing any kind of maneuvers in it.
Do you have plans to automatically connect and disconnect the extending pieces?
Yes, also part of the future work that we are working on right now. We had manually connected all of the spiral zippers when we had done it at Ames, but in the works right now are probe and drogue inspired docking mechanisms, and just to simplify the act of like grabbing and locking, I suppose. This will also have a small, we wanted to use a perception aspect to it to also automate that whole process so that it wouldn't be manually done in the future. But it's a lot of it are still in the works, and we've been going through iterations of that.
So I have a question specifically for the climbing the dune.
Yeah.
What I like imagine, like the guy on the bottom, when he's trying to push the guy to the top, like he would slip, or the same when you're at the top and you're trying to pull someone up, it would slip. So are you guys like working on like any specific ways to like anchor them?
Depending on the bot that we actually use, if we were to, let's say, use the spirit, there's a way to like kind of stabilize it with the way that it's put on there. But part of the project that I did not talk about is the fact that the first section is going to be doing a risk map, also mapping of the area. And so if we're going to try to do a dune maneuver, we would probably position the first bot in a place that is less slippery and then help it go up the more slippery slope as it's continuing forward. So we've got a little bit of information there. But it's more stable on its own.
The moon regulator is usually charged, but is LHS one that you simulate dust being charged? I guess you can't do that.
No.
Yeah, so you assume the problem's gonna be a lot worse than you consider that design or?
What type of locomotion was the best that you tested for this environment?
Like
Like you tested legs, wheels, and I don't know what the Rex legs are called, but other types of legs.
we did not test Rex on our own with the C-shaped legs as it was the tripod gate. That's something we will be doing in the future, but at least compared to the wheeled rover and the Spirit that we did have on site by the time November came around, the legs were definitely better for just getting around and not getting itself stuck. So one of the things we did find is that should you spin your wheels continuously, you'll compact the dirt more and more, and then you dig yourself a hole because it keeps that trench. There's no way of getting back out because it's just all the material's just gone.
Great, let's give Erica a big round of applause. We're going to invite up our last but not least speaker for the day. We have Ahmad here, who is a second-year ESE PhD student. His research focuses on learning for control in unstructured environments where the system or environment change over time, with specific interests in applications to autonomous vehicle. So please give Ahmad a big round of applause. Warm welcome.
Thank you for the introduction and thank you for having us here today. Today I'll be presenting our work on Information-Theoretic learning model predictive control for state iterative learning control. I'd like to thank my co-author Zuri Design and our collaborators Marius from Google and Rahul, whose help and support have been invaluable for this project. So to motivate a bit, the problem that we'll be considering, we'll take a look at iterative tasks that are commonplace in robotics, from applications ranging from pick and place with robotic arms to drone racing for quad builders, or even humanoids in manufacturing where you have to pick and place a certain item repetitively over time. So the goal that we're specifically interested in is maximizing the performance of these autonomous robots for any of these given tasks. And the specific application that I'll be looking at today is autonomous racing, so autonomous car racing. So where we want to iteratively solve for an optimal raceline and the optimal control for that raceline, utilizing previous demonstrations of trajectories as a safety fallback policy. So essentially, we want to ensure safety by complying with two constraints: the state constraints in the horizon, so that could be the boundary or any limits that you have on your states with the speed or acceleration, let's say, and the terminal state constraints, which we want the terminal state to lie in the set of previous trajectories as a failsafe. So to model the system that we'll be considering, we will consider a discrete time nonlinear stochastic dynamical system, where we have our nonlinear dynamics as a function of the current state, the current control input, and some disturbance K. We assume that the disturbances are IAD unbounded, so they are generated from some unknown set W. We have some set of admissible states, X, which we'd like to stay in. And we have a set of admissible inputs that we want to be sure that we're just feeding those to the system. An example of where such a system you consider is anywhere you'd be navigating off-road or even on-road conditions where you have snow or other disturbances that you would not usually hold in your system. So the specific kind of problem that we're looking at is an infinite horizon optimal control problem, where we want to minimize the running cost R of xk uk for all time. The optimal controller would then be the one that minimizes that running cost. The infinite horizon optimal control problem is then as follows. We want to minimize j of x u subject to the dynamics of the system, starting from some initial state x0 and satisfying the state and input constraints. Now, because this is an infinite horizon optimal control problem, we wouldn't be able to solve this as is. We would need to reformulate it into a finite horizon optimal control problem as a means to solving this problem. And we do this by relying on safe sets, which were first proposed by Rosolia and Guerreri. It relies on the concept of robust reachable sets, which are robust control invariant sets with respect to the dynamics and the set of admissible control. So the safe set at any time step t+1 is the set of states that whose next state for all disturbances will stay in the safe set for some control input u in the set of admissible limits. The safe set, we can then define our safe set by union over all successful trajectories. So that's a union over iterations, union over realizations of that certain trajectories, and a union over time until completion of the task. And using now this definition of a safe set, we can reformulate our infinite horizon optimal control problem in the finite horizon one, where now instead of just having the summation over the running cost for infinity, we have an additional term for the value function of the cost to go, where now we want to minimize the expected return of the running cost over the horizon plus the terminal cost, subject to the stochastic nonlinear dynamics, starting from some initial state, satisfying the state constraints over the horizon and control constraints, while at the same time, the terminal set should end in that safe set, so that we ensure that whenever we finish that horizon, we can always stay in that safe set until the end of the finish line, and then we can ensure that we can satisfy the constraints up to the end of the task. The cost to go V is learned from the safe set, and you can learn that with any model of your choice. You can even approximate it by the convex combination of the points in the safe set, but for our use case, we'll be learning it using a neural network, which we'll look at in the next slide. Another preliminary we'll be looking at, which we'll be using for solving this optimal control problem, is Model Predictive Path Integral control, which is involved with the optimal control of stochastic dynamical system. So given a stochastic system and some running cost L in this case, we would like to minimize some expected return over Q, which is a set of controlled inputs that minimize the terminal cost plus the running cost. This is usually solved using minimizing the Gale divergence between the set of control inputs that we sample, which is Q of U, and the optimal control distribution Q star, which minimizes the cost function. And this is done usually using importance sampling. So given the costs of each of the trajectories that you get from the sample control inputs, you weight those trajectories to get the optimal control input for that step. So this is what MPPI looks like. And the key problem that we're looking at is a constrained MPPI. So we'll be using MPPI to solve our constrained stochastic optimal control problem. The current approaches in literature rely either on projection of these of violating trajectories onto these constraint set. And this can be expensive in higher dimensions because you have to project a high dimensional trajectories into its specific set. You can utilize differential flatness to get fast projection of the trajectories, but this requires you to constrict the problem to a specific class of dynamical systems where the dynamics are differentially flat. You can use iterative sampling with high fixed cost on the violations, and that would work, but can be computationally expensive if you have to do multiple iterations at a time. And lastly, you can use control barrier functions as safety filters and cost term, which work really well. But the caveat there is that you need a valid CDL. And in our case, because the safe set varies with each iteration, it requires us to construct the safe set or the CDL for each iteration, which might not be necessarily easy. So we'll look at the two state-of-the-art approaches for solving this kind of problem. The first is with just standard learning model predictive control, which uses gradient-based optimization, where the model must be linear or at least linearizable, and it enforces the constraint explicitly either through chance constraint or through tightened constraints for handling stochasticity. The other approach is ABC and LMPC, which is a sampling-based method for solving the LMPC problem for stochastic systems. It encodes the constraints as cost and reward function, but it's not enforced, and works with simple problems, but for autonomous racing, as we'll see in the results, where we have non-holonomic dynamics, non-linearities, and model mismatch, it wouldn't work in practice. The proposed approach that we're providing is using penalty functions to convert the constrained optimal control problem to an unconstrained one, where instead of minimizing just the cost function on the left, let's say, you add a penalty term on the violations to the function. So the resulting function that you then optimize is the one on the right, where you have the target function plus some penalty functions that you then minimize over. And the main question that you might ask is why penalty function in specific? Well, for one, it results in good approximate solutions for even non-convex functions, and that will work well for us. Secondly, you might ask why not use log barrier functions, and you could. But the problem with log barrier functions is that it results in infinite cost on violating trajectories. And violating trajectories are very likely when you're doing sampling because you're not guaranteed that you're sampling into a safe or constrained set. Lastly, the main issue with exterior penalty functions when we're thinking about classical optimization techniques is that they're discontinuous because of activating in the exterior. And this is not an issue for us because we're using sampling. We don't necessarily need the gradients. So we can just make use of exterior penalty. So to do this reformulation, we first recall the original problem. We had a minimization of the running cost plus some terminal cost, but subject to some constraints. We first define the set distance function, where it's the infimum of the distance between x and all the points in the set C. And then using that definition, we can define the cost on the violation of the state constraints and the terminal constraint as DSL for the terminal constraint for the safe set S, and dx on the violation to the set of admissible states. We then associate non-negative penalty multipliers, lambda x, lambda SL, to each of these terms, and we can then add those as cost to our optimization problem. This is relatively standard work. We're adding just penalties on the violations. This is something that is done in previous work. But the main question that we're trying to ask is, how do we select lambda x and lambda SL to ensure that we can get safe trajectories while at the same time not being too conservative, and we wouldn't be able to learn iteratively for optimizing the race. And the answer that we're proposing is a sampling of the penalty parameters themselves. So in the same spirit of sampling-based MPC, we're also suggesting that we sample those lambda penalty parameters, so we can then have a set of candidate of trajectories that we can study. So the way that we do this is that we first sample lambda x and lambda SL uniformly from a set bounded from 0 to some lambda x max, which is something we can tune, and 0 to lambda SL max. For each sample pair, lambda x and lambda SL, we solve the optimal control problem using MPPI, standard MPPI with now a new cost, where we use importance sampling to where the trajectory is with the lambdas. For each of the resulting optimal controls, now associated with the lambda, so U star T lambda, we check constraint satisfaction. And if the resulting trajectory is unsafe, we filter out those unsafe trajectories. And for the remaining of the trajectories, we find the most optimal of those trajectories that minimizes the running costs and the terminal costs. The result is the following information-theoretic LMPC algorithm, where we first have an MPPI loop where we sample the control inputs, feed them through the dynamic model, and get the trajectories. And then over those trajectories that we sampled, we can then parallelize over the lambdas, where we're evaluating different cost functions for each of those sets of lambdas. And from there, we then apply filtering and minimization over the optimal trajectories that we got from each of those lambdas. And then we can update the safe set after we've done one iteration of the task. Lastly, now that we have a way to solve the constraint stochastic optimal control problem, we then need to learn the value function from these trajectories that we're collecting. And we do this by using a neural network. Specifically, we're using normalizing flow, where the learning will look something like this. Where on the left, we have the true value function learned from the iteration itself, and on the right, the predictions of the neural network on the value of those trajectories. And combining everything together, we have something that looks like this. Where on the right, we have the constraint costs on the boundary violations in our case, and the safe set violating the safe set. We then have the terminal cost on using the value function and its accompanying uncertainty. And finally, we have in green the candidate U star lambda that we've solved for. You can see we have multiple candidates, and then that is the candidate that we chose, which minimizes for the best performance and as well as satisfying the constraints. And the results that we get is that we outperform for a simple point mass problem, where the goal is to get from the 0, location to target in at 6 to 0, while avoiding some obstacle in the middle. So we have some non-convex constraint. And we can see that our approach outperforms the ABC and MPC, which is the state-of-the-art approach for sampling-based LMPC, solving the LMPC problem. So we get a lower lap time, while at the same time still satisfying the constraints. And our approach has less variance in the iterations that it does. Additionally, we outperform LMPC-based LMPC, where we linearize a known model. So we can see that we can push for a lower lap time at higher speeds as compared to LMPC. We can see in more detail in this graph. On the left, we can see that the LMPC hovers around 22 seconds of lap time, whereas the IT-LMPC, which is the method we're proposing, can break the 20-second lap time and achieve high speeds of around 40 meters per second. Additionally, we also compare for the racing setting with the ABC-LMPC, which is the baseline that we're comparing with. And we can see that not only do we get faster lap times, we also can guarantee that we never crash. Shown in blue are the trajectories of the ABC-LMPC that crashed at some point in the trajectory. We can see that for many of these trajectories, ABC-LMPC actually fails, whereas our IT-LMPC remains safe while still iteratively improving on the performance. And we also experimented around with different models to learn the value function. And we ended up with using normalizing flows because they provided the best performance in terms of learning performance and safety. Lastly, we show that we can apply this in real time on a real system. First, we show this in simulation on a loss-based simulation. We show this running in real time at around 80 Hertz. And we show that we can still do a bit of improvement on the performance, even when the LMPC is, or the IT-LMPC is running in real time. And this is the resulting trajectory after we let the whole pipeline go until completion. And finally, we did an experiment on the physical system. And this was the experimental platform that we used to do the experiments, where we have some localization from a GNSS, and we have the map that was shown in the previous slide that we want to optimize the LDA for. And we still are able to do the IT-LMPC even on a real system. This was at night, so it's a bit dark, but the system is still able to learn and perform in real time the safe iterative learning, while at the same time ensuring safety and improving performance. And lastly, as a bonus point, we can also, because this is a general approach for handling constraints, it's not necessarily limited to the specific problem that we have with LMPC, where we're just focusing on the safe set. We can also extend this to handling obstacle constraints, where we'll see now in a few seconds that even when we introduce obstacles, we can easily encode that as another distance and another lambda that we sample over. In addition to minimizing the lap time, we also can avoid the obstacle and avoid crashing into that static obstacle in this case. So that is everything. I'll take any questions. Thank you.
Was there any work that needed to be done to transition from your simulation results to your experimental results? Was it just a one-to-one went on really easily, or were there things you had to do to make it work for your hardware?
There was definitely some SysID that was involved, because again, this is still a model-based approach. So you need a good model to be able to do experiments. But we had to tune a bit on the covariance of the samples that we were doing, but more or less it was pretty easy to do the transfer. And we even tried with learning the baseline in sim and then just deploying that baseline in the car, and that worked relatively well, I would say.
So in sim, I saw that there was like a track almost, but in real life, it didn't look like there was like some sort of track. So
yes. So the boundaries, the on-car experiments are still preliminary. We'll do more experiments. The boundaries in the real world are virtual. So we're having limits in the software to detect when we violated those constraints, and we just killed the controller. But we will have boundaries with more experiments. This is just a preliminary result of this. Yes.
I'm not sure if you mentioned this, but what is like the frequency of the control, since you're using like a sampling-based method? I know you're parallelizing over different parameter choices, but I would guess that it would require more significant compute power than other methods.
Right. So we're using a Jetson Orin in this case in the real world experiments. We're running with 1,024 sample trajectories with 16 lambdas that we're sampling, and with all of those constraints, we're still able to get 40 hertz of compute in real time. You could definitely do better. Our code is not perfectly optimized yet, but it is possible because we're using the GPU that's on board the Jetson. That's the key part with sampling-based MPC is you can utilize the parallelizability of the GPU to do the sampling. Any other questions? Yes.
Can you explain a bit how you mentioned you sample from the value function using normalizing flow? I guess sort of like roughly how does that work?
Right. So for each of the sample trajectories, so these points are the sample trajectories as just pure states. We see that for all of those trajectories, we evaluate only at the terminal state the value function because that's the terminal cost that we're evaluating. And we feed that through the normalizing flow in parallel. So we take all of the terminal states, we feed them through the normalizing flow, and we get both the mean of the predictions as well as some uncertainty for it from that normalizing flow. So that's primarily we're using it.
Saw that you like filter out like unsafe trajectories, but how do you actually figure that out?
Right. So because we have a distance measure on violation to each of the sets that we want to stay in, then we have an easy way of checking whether or not a state is safe or not. Because we can check if once we've sampled the trajectory, like in this case, we can see if the trajectory goes out of bounds. And that one we can just check because we know the states after we've sampled. We can just do it. You can be more robust in your filtering if you have some more uncertainty you have a model and be more strict in the way the filtering that you do. But that's just a trade-off.
Wonderful. We do need to get everyone going. Thank you so much.